And I'd like to recap and see what we did yesterday as we start up. And we'll just take a few minutes to get set up on AWS. So to recap what we saw yesterday, we saw how Tau can be used to launch an application which is unmodified. There was no change to the source code, the build system, or the binary. We just simply launched an MPI job using MPI run Tau exec, some options and some environment variables, and then the application binary. We also saw how we can use Tau in a container setting. We have Tau installed in the Singularity container, but we just barely touched on what the containers are. And for some of you, it may have been the first time you are actually running a large container on with an MPI job. So I want to go through the basics of what containers are. How do you build your own container? How do you use base container images that are provided by E4S to build your own system? And how you can leverage the work done in the E4S project, whether it is tool integration with Tau or other numerical libraries, to create a custom environment for your job. So with that, I touched briefly on what containers are, that you have a container-based environment where there is no additional kernel running. You just have the host bare metal operating system, and then you have on that operating system a container without the Linux kernel. And with this, you have all the libraries that are built for the OS within the container without the kernel. Now let's just look at what these containers are and get an introduction to Docker as well as Singularity. So I will switch to using, just a second, let me increase the font and I hope you can see this better.
Online, it looks good. Thank you.
Okay, good. So here, yeah. So let's go to the SRC demo directory. Containers. So CD to the this /src demo containers, and then cat the readme file. Now, just wanted to make sure that everybody was able to get an instance. Go to e4s.io/tutorial and then get an instance and then go to the login. Is there anybody who's having trouble in connecting to these instances? And then you can launch a terminal window and go to the SRC demo containers directory and then cat the readme file there. It will show you step by step. What I want to start with is, how do I create my first container with Docker? How do I create a Singularity container? How do I use MPI in a container? And then once you have this, how do I then transition to the E4S containers? And we already saw how we can do replacement of MPI within the containers, but this is just taking a step back and showing you how we create the first container. So I will go and run these commands. So with containers, let's start with the Docker. Docker is the most prevalent container runtime out there. And to create your first Docker container, you have to create a file called Docker file. And within that, you must start with a base image and then add an application to that, a source code, for example, compile it, and then create a binary that you can then launch with the Docker run command. So in case you're just joining us, we are again at the AWS instance. We have gone to e4s.io/tutorial, this web page, and then we reserve an instance and launch it like we did yesterday. And then we can go to the CD, to the SRC demo containers directory, where we will create our first Docker container. Okay, so again, this is e4s.io/tutorial. And if you'd like a head start, please go ahead and try the commands in the README file as we catch up. Okay, so let's get started. If you want to create a Docker container with MPI, what are your steps? I will take a simple example, but not too simple. An example that uses MPI and just does a print statement so that I can run it with multiple MPI ranks. And to do that, I will create a first Docker file. So over here, you can see that we have base images as well as full-featured containers. We saw these yesterday. We launched the Singularity container for a full-featured container. But today we'll start with something very simple. This is a Ubuntu 2004 container from the Exascale Computing Project's E4S. What is interesting about this is that it has MPI in its path. It has tools like CMake in its path, but nothing else. It's a bare bones container meant for you to create your own custom images, which are compact, and you can start with a simple program like this hello world.c. And in this hello world.c, I can compile it using MPI-CC. So once you launch this AWS instance, cd to this directory, cd to src demo containers, okay, and then cat the Docker file in this directory. So what am I doing here? I'm saying take the hello world.c file that's in the current directory and copy it to a directory called /app. Then cd into that /app directory and use the MPI-CC, which is already in your path from this container image, and compile this hello world.c to create app/hello. Okay, what is this hello world.c? Let us look at it. It's a simple program like this. It has mpi.h, standard.io.h. It does a com size, com rank, and then gets the host name and says hello from this rank out of so many ranks on this host. We do an MPI barrier and then MPI finalize. In this hello world application, how do you run this application normally on bare metal? You would say MPI-CC hello world.c, which gives you, say, hello. And then you typically run it on the bare metal instance using MPI run. And you could say MPI run-np4 hello. We all know this with a simple example. And if it doesn't have enough resources, you can just say oversubscribe like this. And then you will see that it creates the hello executable running on this bare metal. Now, in this directory, I have this Docker file, and I copy this hello world.c in an app folder. I compile it with hello world and create this app hello. And then to run it, I need to build the Docker container. And to do that, you can see that in the README file, I have this command called docker build, and then give it a name, a tag. And so here, this is the new name called my hello MPI, and I'm using a tag of latest with the dot. What this dot does is it looks for the Docker file in this current directory, and then it will build this container. So I can do Docker build like this. If you have any problems in cutting and pasting, in this terminal, I use Control-Shift-C and Control-Shift-V. Or you can always go and highlight and go to the edit, copy and paste. So let's build this container. And the first thing it does is it gets the Ubuntu 2004 latest. It uses the cache. It runs this command. And at the end of it, it will create a container called my hello MPI :latest. You can also give a date or something here. Just a sec. Connection was closed. That's odd. I need to log in again. Okay. So here it is. If I say Docker images, let's say Docker images, grep for this my hello MPI, I should find this container loaded on my current instance. It's not on Docker Hub, but it's just locally on this my hello MPI. The latest. Now, how do I run this container? I can say Docker run as is shown in the command over here. I say --rm, which is to tell it that please clean up after yourself when you exit from the Docker container. Don't leave your images around. And then the interactive mode with a tag of my hello MPI :latest, the one which I just created. So this is creating this tag. This is now using that and running this image. So let me just try this over here. Now, how do I know I'm inside the container or outside the container? First of all, if I look at the cat pt1 release, on the bare metal, I'll see that I'm on AWS Amazon Linux too, right? If I look at the uname -a, it will show me the kernel that it's running. It is a 5.10.130 kernel on Amazon. So if I were to say Docker run with the --rm, with the -it my hello MPI :latest, now I'm going inside the container. And you will see that I will have a prompt which takes me inside the container. And now I will be able to query what operating system I am on. So with this, I can say cat pt1 release. And you will see that now I'm not in Amazon Linux 2 as I was before. I'm on the Ubuntu 2004.5 LTS. So I have the same kernel, but I'm using a different operating system. How do I see the kernel? I can try this uname -a again, and you can see that it's the same kernel, 5.10.13, the Amazon kernel, with a new operating system, which is Ubuntu. And I should now have within the app directory a hello executable. This was compiled when I did the Docker build. So I can run now this hello executable right here within the container. And there it is. It's running this on this image. You see the host name 0, 1, 2, 3 out of 4. Yes, it is on. Yeah, okay. So I'll just... So any questions so far? What did we do? I can come out of this container using exit, and I can again show you the Docker file. And this is the first Hello World container where I have taken an MPI application, injected it inside the container in the /app directory, created a binary called hello, like this, and then run it and launched the MPI run, and I was able to do this. Okay. Any questions so far with just Docker? Because next we'll look at Singularity and how we can go from there. Now, I should mention that you can create an account on Docker Hub and share your container with others. And how it really works is you can look at a container that you have and say Docker login -u and then user ID. And then you give the password. And then you can say Docker push my hello MPI :latest. And this way you'll be able to push the my hello MPI image on to Docker Hub. And someone else can then say Docker pull with your login /my hello MPI :latest, and they will be able to get that image. So if I had a login account, say Docker login -u Samir Shende, and then I give my password, and then I said Docker push my hello MPI :latest, then I would have pushed it to Samir Shende /my hello MPI :latest, so that if you wanted to pull this container, you could just say Docker pull and then say Samir Shende /my hello MPI :latest. And then you would have that container locally, and you will be able to say Docker run on that container with the --rm, and then you could say -it and say MPI :latest. Okay. This is just local. If you were pulling it from Samir Shende, you will have to qualify it with something like this, Samir Shende /my hello MPI. But here I have the Docker container, and then I can run app hello like this. So I'll just wait for a minute and see if everyone can confirm that they are able to run the commands written in the README file for Docker build and Docker run in this src demo directory, src demo containers directory. And are there any questions? Did anyone have any trouble running this? Is this okay for containers? The tutorial? Yeah. Now, for security reasons, many supercomputing centers do not run Docker, and they prefer to use two alternatives. One is to use Podman, and the other is Singularity, which is very popular. Also, an offshoot called Aptainer is becoming popular. But it's the Singularity /Podman, which is deployed on many systems. Now, what is interesting about Podman is that it provides the same interface as Docker. So you may not even know that you're using Docker or you're using Podman. Podman comes from Red Hat, and it is more secure in many ways than Docker. if you noticed, I did not need to become root to build this container with Podman. So with rootless, I was just able to say Docker build, Docker run with my container, and I just used the commands. Now, what you may find interesting is that if I say Docker -- version, you'll see that it is actually Podman under the covers, right? So we were just using Podman all along, but it has the same Docker interface. This is Podman version 3.0.1. And so you do not need to have root access to build containers or to run the containers. You just can pull, you can just build, and you can run the container. This is the first MPI container. And our E4S project at E4S.io has many such containers available for download. If you go here, you'll find that we have base images. These are base images. They are minimal Spack images, and this is the ECP E4S Ubuntu 2004 container that I just used. I did a from ECP E4S / Ubuntu 20.04 latest, which is the minimal Docker container. We also have GPU containers with base images. And with these base images, we have the vendor runtime integrated in it. So we have a base image for ROCm 23.02, which has ROCm 543 in it. And it has CMake, it has Make, it has GCC compilers, and nothing else. So you just have the vendor runtime and the bare bones GPU-enabled container that you can then add your MPI application to, use your HIP runtime, and create your own application that can be launched on a GPU. And Cetonix has Singularity installed in it with even support for MPI. And then you can launch that container with the srun command and launch it on a node which has a GPU, like a GFX90A MI250X GPU. And you'll be able to use that with ROCm 543 with this base image. So go ahead, Mark.
Samir, sorry, maybe you said that. Apologies, I was late this morning. But so with these base images, with the compilers and imagine MPI libraries as well, if we deploy on a Cray and build with the compilers in those images, they will be able to run it. The MPI application will run with parameter performance out of the box.
Yes, so you will be able to then use E4S CL to launch the container.
Yeah.
And while we are still working on that because of the downtime, it's not perfect, but we are getting there.
Yeah.
And you should be able to create that. And with this simple example, I also wanted to mention that with the base images that we provide in the E4S project, you can then create a very compact container. You don't need to create a container like we do with a full-featured 100 packages in it, kind of an image, which may be large. So you can start with the most compact image with the ROCm runtime, which works with the GPU, or with the CUDA runtime for the NVIDIA GPUs. So both options are available. And then you can create your own custom image like we just did with Docker, and then launch that container. Now, I also have another project that...
Samir, sorry, I have one more question on it. So one on MPI, so these base images, do they have MPitch or OpenMPI? I mean, just out of curiosity, I know that
they have MPitch on it.
MPitch, okay.
Yeah.
And then I had another question, which I'm trying to remember. Never mind. I'll come back when it.
So that's actually a good point. You see, we had to choose between MPitch and OpenMPI, but on the Cray systems, your default MPI is Cray MPitch. So if we started with a container that has MPitch in it, then we won't have to do the Y4 MPI switch at runtime where the API calls are changed in some way. In this case, it will be just a drop-in replacement using the MPitch application binary interface. And so it is just a question of setting LD library paths in the E4S CL. And so it's much closer in performance with the actual MPI. That's why we have chosen that MPitch to start with.
So we for MPI as a performance hit, do you have an
It's a
idea
marginal
measure?
performance hit, but when you run a large application on many nodes and it's running for minutes or hours, then the slight change in moving a MPI communicator call from here to there will be so limited that you will not even notice it. It's only in something that's running for like 2 seconds that you may see the slight increase in dilation in the runtime.
Thank you. The other question is actually on Spack.
Yes.
So I guess these base images also ship with the Spack.
They do. Installed. They have Spack in them, and so when you use it, you can.
So for the Spack configuration in these images, is it aware of the binary cache mirror that you have developed for E4S? So let's say if you Spack installed something that has already the binary in the cache, and it's the right combination of compiler.
I think you have to choose that because there are multiple mirrors over there.
Oh, okay.
There are multiple mirrors, one which hosted on AWS by the Spack team, another hosted by organization. So we provide one mirror in the E4S project, mirror.e4s.io, but we don't force it.
You don't force it, so you don't
force it. So you have to yourself add the mirror, and then you have to do that.
The reason why I'm asking is because I actually had browsed the collection of packages a while ago, because in the domain of bioinformatics, there's a lot of appetite for further improving the reproducibility and actual deployment time of applications via Spack eventually to optimize for the architecture. And so I was seeking for existing Spack mirror projects with collections of bioinformatics packages and couldn't find one. So that's why I was asking a bit about that. I mean, I guess the main thing I would be looking after in the space is knowing that those packages would build correctly with the given configuration, so they kind of been verified. So, or even you have the binaries available.
So the good news is in these base images, I stand corrected. There is the mirror.spack.io as well as the cache.e4s.io mirrors already integrated in the base image, as you can see in the Spack mirror listing. There was a time when it was not there by default, and so I said that you have to manually add it, but this is now all equipped so that if you set a Spack install, it will access the mirror and see if it's there in that.
Yeah.
So both those mirrors, one hosted on AWS by the mirror.spack.io, as well as the one hosted at the University of Oregon from the cache.e4s.io are there. And Spack is there in the container. So it's very easy to install other packages as well. Now, although this project is not ready for prime time yet, I want to show you what's coming down the road. There is a project that we are working on, and it is the E4S ALC. This is a new tool. It is a tool called a la carte. What this allows you to do is it allows you to say, this is the base container. These are the packages I want to inject in it, and create a new container with this name. Very simple tool. You say, start with this, add this, create a new image with this name. And then it will take care of reading the input that you have given it, and it will create a new container. You could say, start with this image called CentOS:8. Create a new image called myCentOS image. And then add the NumPy package or add the autodiff package from Spack. It can inject Spack in it. It can add the Spack packages. You can say if you don't want a Spack, you can say no Spack. You can even give it a JSON file where it says, start with this image, create a new image called Kokos Raja, and then add these two packages called Kokos and Raja from Spack. That's it. And you can also specify other operating system packages, and this is unique. You can say, I want to add NeoVim and Valgrind as tools that you should install from a yum install or a app install command. It figures out based on the operating system which package manager to use, and it will just install the OS level packages. And you can go one step further and you could specify a tarball. You could say, also take this tarball located here in this web address and expand it over here in the op directory. So it will take all those three things and create a new image for you. So it's a very simple tool. We are working on it, and it's available in a beta right now. But next time we have another tutorial, it may be ready for prime time, and we may be able to demonstrate it on your system. So it's a tool that kind of finishes up the process of starting with the base image, adding new packages to the base image, creating a new container for you. So you don't have to worry about doing the Docker file and building it and then doing all the commands yourself. It will take care of the Spack packages. It will take care of the operating system packages and other tarballs that you want, and just help you along in creating your own custom containers. Any questions about that? Is that okay online?
Doesn't look like we have any questions online yet. Yep, looks like thumbs up. All good.
Thumbs up. Okay. I believe we are also working on a way to provide support for Singularity. So if you have a ability to do a Singularity build on your systems here, you could start with a base image of Singularity, then add these other packages and create a new image. So it will be a a la carte selection tool where you just say, I'm just picking from this menu of packages, and I'm just picking these two additional packages that I want to add to this base image and create a new image. Now, starting with Singularity, how does that work with the Hello World basic container application? And you can see this in this README file that I can create a definition file, an Ubuntu MPI def file. I can then build an SIF image and start with this definition file, and it will create the new image called .sif over here. So let me just start with this Ubuntu MPI.sif file. What did I just do? I meant to cat Ubuntu MPI.def file. And it's a very simple container. I'm just saying echo in the run script area so that when I launch this container, it will just run this command. And so I can then say sudo bash. I specify the same HPC Linux 12 exclamation password. I become root. So I'm here. I can look at the Ubuntu MPI.def. And this is what happens when you run the container. And then I can say Singularity build. First of all, let me just get rid of the original SIF file here, which is Ubuntu MPI.sif. I remove this file. Now I can say Singularity build Ubuntu MPI.sif with Ubuntu MPI.def. Is that okay? We are just saying start with this Ubuntu image like we did with Docker file, and then use this def file which describes this, and then create a Singularity image called Ubuntu MPI.sif. So it's building, and it gets the image, and it will create the full file, the .sif file, which you can then use with Singularity. Are there many users of Singularity at Pawsey? Is it catching on? Yeah.
Yeah, we have a lot of users in the bioinformatics.
In the bioinformatics, and are they building their own containers?
Bring their own.
Are they building their own containers, or are they using containers that somebody else has already built?
Most of them are using.
Yeah, I can comment.
Yeah, most of them are using containers that were already built somewhere else.
Were already built somewhere else.
Yeah, but it's not only isolated to bioinformatics. We have users from many other fields using containers, and many of them are building their own containers also in radio astronomy research and the open foam.
Okay, great.
So it's a very diverse use of.
So then a tool like E4S ALC that can take an initial container and just add a few more things to it and then create a new image may be useful in this setting where they say, I love this container, but it doesn't have Valgrind, and I need Valgrind, but I don't want to go and figure out how to do this. This would be a tool that would help them with this ALC. You just specify this and say, I can just add this, or say, I want to expand this data set and ship it as part of my new container, starting with the container that's already there. So this tool could then help those users.
Very, very attractive, yeah, for sure.
Okay. Yeah, I think it can be indeed interesting. I mean, we have different tiers of users. I think the ones that are a bit more power users are the radio astronomers, and they have Python workflows. So, I mean, of course, they develop some of their software stack as big Docker files with lots of embedded applications. But I think the flexibility of having a tool that provides just a command line interface for adding more, I think is very interesting for them, especially for bioinformaticians. We take a different approach, so we try to leverage as much as possible the biocontainers initiative, which is cows into Bioconda, basically. And to that end, we actually also use that tool by Vanessa Sosha that I presented a couple of years ago at the tutorial, SHPC. So we basically provide the system-wide installations of the biocontainers, but then they are exposed as modules. So basically they go module load blast, and they run blast. Under the hood, it's containers. But we use these wrapper scripts that just hide the Singularity syntax, so that they don't even have to bother learning how to use Singularity, or it will be Podman one day probably. Yes. So that's what we do for the beginner users. But then we definitely have user cases for a la carte containers. I was saying probably in the physics domain or the astronomy that may be very appealing to them. There's probably something to advertise. Even at the ISC, probably we should start and mention this as working. Well. Yeah.
Yeah. So I just wanted to give you a preview that this is one of the things besides the E4S CL, which is also very similarly named the container launch tool. With this E4S ALC, will give you the full spectrum of the tools, where you can start with a base image from E4S. You can inject new things in it, create a custom image, launch it, and replace the MPI in that image. And without having to learn about Dockerfile
And that's the point. Yeah, I think the ecosystem you're building around containers within E4S is amazing. It has a lot of interesting functionalities for the end users, actually, to make their life easier.
Easier, yes. And we also providing base containers as well as a bare metal install for all of these packages, so that it's available on the system. And if you want to see how it is used on other DOE systems, we have a dashboard .e4s.io, which shows you exactly the SPAC recipes to bare metal install it on various machines. And you can see exactly how this recipe for E4S is there in the SPAC.yaml, the results of the test suite for running the test cases, where it's not just enough to install the packages, you need to also validate them with a compile and run with GPUs, with MPI, say running a simple test example on 8 MPI ranks and verifying that Adios 2 package was correctly installed with a pass-fail notification. So we do this on various machines. These are machines at Oak Ridge National Labs. These are machines at NERSC. And some of them are at Argonne with different compilers. So
the test with the test suite, Samir, do you provide the actual inputs and scripts that form the tests? And do you have a kind of a template for the type of tests you run for each package? Or is there kind of a pattern there? Or?
This is actually a test suite under the E4S project. And you see over here the E4S project on GitHub.
Oh, yes.
This has the test suite with the validation tests. So here in this validation test, let me just look at a whole bunch of these tests. Here is a test for, say, HDF5. So within this HDF5, every directory has this same format where it is a clean.sh, compile, run, and then setup. So the clean and compile and run use the setup. And you can see this with other test cases. There's a full LLVM test suite, which has, Fortran tests, and there's a full G-Fortran suite. There were 3,900 entries for the entire Fortran test suite. So you can see that it's a very extensive validation test suite with all of these packages that are there in E4S. So this is for, say, Cabana, and this is the Cabana test suite. So this is a simple example, but not too simple. So here there's an MPI, and you can see that there's some computation that it performs. And then there is a compile.sh, which says exactly how is this built with the setup.sh. And then there is a typical run.sh where you can run this example.
It's very interesting also. This is a very precious in itself, I think. I mean, it's a resource that other centers could also leverage for their own testing of applications.
And so
we do use Reframe at Pawsey, the framework by CSCS in Switzerland.
Yes.
But I mean, it's just that basically we use Python scripts to specify what happens in the test. But otherwise, I think it's very interesting. Deva is actually, I don't know if he's on the call today. Deva has been leading the effort on Reframe for long. Basha is also involved, right?
I'm here.
It's very interesting.
Yeah. I came back, yeah.
If there are some other comments online, please feel free to unmute yourself. We would love to hear from folks here if some testing like this would make sense for some of your projects too.
Hi, Marco. Yeah, thanks. Yeah, we have been using reframe testing for our acceptance testing while returning the system from the maintenance. So I think this is a good idea to use this test suite, rather than creating our own tests and running them. So yeah, it is really a good case to use this one. This application.
Well, we are hoping that we'll be able to, with the ROCm 543 installation, once we have that with the new compilers, with the Cray programming programs installed with the support for 543, we should be able to install the full E4S suite again with the latest ROCm features. We have it for 502 right now on Cetonix, but it will be even better once we get that update. Cetonix is back. Okay.
Yes, and we have ROCm 543 on Setonix as well as a module.
Now the 544 was just out last week, I think. So we need to keep the pace.
So here you can see that after you do the build of the Singularity container, you can then access it